In the earlier session, we looked at binary search trees, saw how to work with them, saw the properties of the binary search tree, and observed that in a binary search tree, if you want to query or if you want to insert or delete, in the worst case, the performance is of order n, which in a way is not better than the sequential search. Like suppose you are given a sequence of keys and you want to find a particular key, rather than doing a tree structure, we can just sequentially try to find a key. Like for example, if I have a sequence like some arbitrary sequence, and if you want to search for some key in this sequence, there is no need really to construct a binary search tree with these keys and then try to query the tree. One can just do a sequential search and achieve the same complexity as the worst case of a binary search tree. So, binary search tree as they are defined are really not the answers if you want to do a search efficiently. So, this particular session we try to look at how one can rectify this problem. We also have seen that if a binary search tree is full binary search tree, then the search is efficient. For example, let us illustrate this point. If I look at a binary search tree say with 7 nodes or which is going to 7 keys, then we have seen that there are 2 possibilities. The worst possibility is when your binary search tree is completely a skewed binary search tree. That means your 7 keys are going to be something like this, 4, 5, whatever, 6 and 7. So, if I have this is 1, 2, 3, 4, 5, I can have another 2. So, this is a skewed binary search tree. In this case, we know our performance is going to be like the worst case performance. But if our binary search tree is not structured like this, but is structured in a more balanced way, or is a full binary search tree like in this case, correct. So, these both are binary search tree with 7 nodes. In one case, the height is 6, whereas in the other case the height is 3. And we have seen that all operations in a binary search tree are proportional to the height of the binary search tree. So, a tree which is unbalanced or skewed gives us the worst performance, whereas a tree which is a full tree or we will say a balanced tree will give us the best performance. So, while rectifying binary search tree, this is the crucial property that we will try to work with, is how do we keep height of a tree bounded. So, when we say we are going to correct this problem or try to rectify this problem, we are going to try to see that the structure of the tree is so that height does not go beyond a certain point. So, that whenever you want to query or you want to do any operations, they happen in a efficient way. So, for correcting this, we use a height balancing property, which says that for every internal node of a binary search tree, the heights of the children of this node can differ by at most 1. So, what we are doing is we are starting with a binary search tree, and for every internal node, we look at height of its left subtree and height of its right subtree. This cannot differ more than 1, or this can differ at most by 1. We say that this is a height balancing property. It is a property that basically characterizes the structure of a binary search tree. The binary search tree property characterizes the way keys are going to be stored in a binary search tree, whereas the height balance property is going to characterize the structure of the tree, which is going to make the search efficient. So, any binary search tree that satisfies height balance property is called an AVL tree. AVL happens to be the initials of the inventors who first worked with this particular structure, Adelson, Minsky and Landis. So, AVL trees basically are binary search trees which has this added height balancing property. You will see that this plays a very crucial role on the height of the AVL tree, and that makes it an efficient data structure for searching purpose, for searching applications. Just an example of a AVL tree. So, first an AVL tree has to be binary search tree. So, we will check first whether this is a binary search tree. So, if you look at the keys that are stored in the tree, we can easily identify that this happens to be a binary search tree. So, let us maybe check this for a particular random node. So, if I look at this 78, then its right subtree has all the keys bigger than that, and its left subtree has all the keys less than 78. This can be checked for every other node. So, to begin with, this is a binary search tree. Now, we try to look at all internal nodes and see whether the height balance property is satisfied at that particular point. So, we begin with the root. So, the height at the particular of this tree is 4, is 1, 2, 3, 4, that is the longest path in your tree. Again, by convention we will always use leaves as null nodes. So, these are acting as placeholders. So, even if the diagram does not always show the null nodes, we will always assume that null nodes are there at the end, at the last level of the tree. Now, let us look at its subtrees. Now, this 44 has a left subtree. If I look at the height of the left subtree, it is 2, and height of the right subtree is 3. So, at this particular node, that is at the root, its left subtree has height 2 and the right subtree has height 3. So, difference is 1. Now, this has to be checked at each node. Now, let us look at this node 78. Its left subtree has height 2, right subtree has height 1. So, it is satisfied at this particular point. Let us look at 17. At this particular thing, its right subtree height is 1, whereas left subtree height is 0. Again, the difference is 1, correct. So, we have seen that at all internal nodes, the height balance property is satisfied, and this also happens to be a binary search tree. So, this is a binary search tree which has the height balancing property, and so is an example of a AVL tree. If a tree is not binary search tree, then even if it satisfies height property, it still is not an AVL tree. So, any tree which is not binary search tree, one need not even check height balancing to find whether it is an AVL tree or not. Let us try to look at an example of a tree which is not an AVL tree and which essentially violates the height property and not the binary search tree property. So, what we will try to illustrate is a binary search tree in which the height property is violated. So, let us start with the same tree and try to work out. So, you can have 44 the same key, and you can have 78, and if the key 88 was not there, so in the same king, if correct. So, let us consider this tree. Now, this is easy to check, is a binary search tree. Now, let us look at the height properties. At this particular node, height of this node is 2, right. Height of this subtree is going to be 1, 2, 3. So, height balancing property is satisfied at 44. Now, let us look at 78. Now, 78, its right subtree is just the null node and its height is 0, whereas if you look at its left subtree, its height is going to be 2, correct. So, what we observe is that height property is violated at 78 or this particular node. So, this is an example of a binary search tree which is not an AVL tree. A few simple observation. If I have a subtree of an AVL tree, then it is always an AVL tree, because the definition is recursive. So, if at a particular node your height balance property is satisfied, then it is also satisfied at roots of both the left and right subtrees of that particular node. So, the left subtree and right subtree are also going to be AVL trees. So, very trivially or very simple observation is subtree of an AVL tree is always an AVL tree. This is going to be a crucial observation when we try to prove the important consequence of the height balancing property. The important consequence that we are going to prove is that the height balancing property basically keeps the height small. We will see exactly what small is going to be, and crucially that fact is going to come from the height balancing property. So, this is an important idea that we are going to prove, that height of an AVL tree storing n keys or n items is order of log n. That means an AVL balanced tree or an AVL tree is like a full BST. If a full BST is also, the height is going to be of order log n, and so AVL tree is like a full binary search tree. So, we are going to try to prove this fact. So, the proof is going to be by induction, and we are going to let NH be the minimum number of internal nodes of an AVL tree of height h. We are going to find a bound on this, and that will be used to interpret the bound on the height of the tree. We know if we know nodes, number of nodes, then we can interpret about height and vice versa. So, we are going to try to find a bound on number of internal nodes in a AVL tree of height h, and this in turn will be used to bound the height of the tree. Now, can we very easily observe that when h is 1, the minimum number of internal nodes is going to be at least 1, and that precisely is the case when I am going to have only a tree with a single node, which is going to be the root of the tree. So, this is a AVL tree of height 1, and it will have at least one internal node. Now, if I look at N2, that is a tree of height 2, then it should have at least 2 internal nodes. It should have 1, or it can have a node like this, or it can have the other possibilities, a tree like this. So, these are the two possibilities when height of the tree is 2. What you want is the minimum number of nodes. So, it has to be at least 2. So, N1 is 1 and N2 by 2 can be just proved by observation. Now, let us look at a tree whose height is going to be bigger than 2. Now, any tree, AVL tree of height h bigger than 2 with minimum number of nodes is going to be a tree such that the left subtree and right subtree are also AVL trees with minimum number of nodes. So, what we are saying is for h bigger than 2, AVL tree with minimum number of nodes is such that both its subtrees are AVL trees that we have already observed, and they also have minimum number of nodes. Now, such an AVL tree is going to obviously contain the root node, one AVL subtree of height h minus 1 and other of height h minus 2. Excuse me for a typo. This is height h minus 1 and not n minus 1 and n minus 2, but height h minus 1 and h minus 2. So, sorry for the typo, heights are h minus 1 and h minus 2 and not n minus 1 and n minus 2, as the picture shows the correct values h minus 1 and h minus 2. So, we are looking at an AVL tree of height h. So, if I look at this AVL tree, this height is going to be h, and if it has to have minimum number of nodes, then the subtrees should have minimum number of nodes, and that means one should have height h minus 1 and the other should have height h minus 2. So, once we observe this, that means n h is going to be 1 plus n h minus 1 plus n h minus 2, that is the minimum number of nodes, internal nodes of a tree of height h is going to be 1 plus the minimum number in h minus 1 plus minimum number of nodes in a height of in an AVL tree of height h minus 2. Now, if you look at the relation, this is a recurrence relation, n h is equal to n. So, height number of nodes in a AVL tree of height h is expressed in using the number of nodes in height AVL trees of height h minus 1 and h minus 2. So, that is a recurrence relation. It is very easy to observe that if I look at n h, it is going to be an increasing function of h. That means, if h 1 is bigger than h 2, right. So, it is easy to observe that if I have h 1 bigger than h 2, in this case n h 1 is going to be bigger than n h 2. That means, this is an increasing function of h. Or in other words, if I take h 1 as h minus 1 and h 2 as h minus 2, I can infer that n h minus 1 happens to be bigger than n h minus 2. From the fact that n h is an increasing function of h, we can conclude that n h minus 1 happens to be bigger than n h minus 2. Now, using this fact, we get n h to be bigger than 2 n h minus 2. So, in the earlier expression, we are simply going to replace n h minus 1 by n h minus 2 and drop 1. Right. So, if I look at the earlier expression and this, I am going to replace n h 1 by n h minus 2 and drop 1. Now, we are going to use this recursively. Now, I can use the same fact and say about n h in terms of h n minus 4, n h or number of internal nodes in a tree of height h minus 4 and so forth. Intuitively, what we observe is, as your height decreases by a factor of 2, that is your number of internal nodes grow exponentially. Right. So, what we observe is, as I move from h to h minus 2, you get a factor of 2 here, and as we move from now h minus 2 to h minus 4, this factor moves to 4, and as we move from h minus 4 to h minus 6, this actually becomes 2 cube. This is 2 squared and this is 2 to the power 1. So, what we observe is that as your height moves from h minus h to h minus 2, h minus 2 to h minus 4, your factor, constant factor, increases by a factor of 2, and so it grows exponentially. So, it can be easily proved by induction that n h happens to be bigger than 2 to the power I n h minus 2 I. Now, we try to use the base case in which we know n 1 and n 2. Right. So, we are going to choose an I such that h minus 2 I is either 1 or 2. So, I can choose, say for example, I to be h by 2 minus 1 if my h is even. Correct. So, if h is even, I can choose I equal to h 2 minus 1, and then h minus 2 I would become actually n 1, and we know n 1 already. Otherwise, it will become n 2. Correct. So, we can now choose I either as h by 2 minus 1 in case h is even, or I can I choose the box of h by 2 minus 1 in case h is odd. In either case, I will get n1 or n2, which we already know is either 1 or 2. So, putting this in your equations, so if I put this fact here, one can actually do some algebra and prove that nh is bigger than 2 to the power h by 2 minus 1. So, I am simply going to put I equal to h by 2 minus 1, and then we know this is precisely 1 or 2, depending upon either h even or odd. Now, simply taking logarithmic on both sides, what we get is h is less than 2 times log n h plus 2, or what we can prove or we observe is that height is bounded by logarithmic of n, or if I look at height of a AVL tree, it is bounded by factor of log n. So, we say that h height of a AVL tree, which is going to store n items, is big O of log n. Right. So, this is simply taking logarithms and changing the signs. So, this is a very important result that we have proved, that height of a AVL tree is always, if it is going to store n keys, is going to be always of order log n, and that is like the best case of your binary search tree. So, an AVL tree represents sort of the best case of your binary search tree. So, if you want to query a binary search tree, we know it is going to be proportional, the time taken to query is going to be proportional to the height of the tree, and which we know is order log n. So, in the worst case, your search is going to be of order log n. Right. This is a substantial improvement over the sequential search, which we know takes order n time. So, that overcomes the shortcomings of binary search tree in terms of the height of the binary search tree. So, the height balancing property has rectified the shortcomings of the binary search tree. Now, we look at the update operations in an AVL tree. Right. Suppose you have an already present AVL tree and you want to insert an element into an AVL tree. Then there are two important things that one has to look at. One is, we have seen AVL tree has two key properties. One is the binary search tree property and other is the height property. So, if you want to insert into an AVL tree, obviously you want an AVL tree back. You do not want to lose the structure of an AVL tree. That means, your new tree should be a binary search tree and also should satisfy the height property. So, insertion in AVL tree has to satisfy two properties, a binary search tree property and the height property. So, to begin with, since an AVL tree is a binary search tree, your insertion is done as you do in a standard binary search tree. That is, the key that you want to insert, you search for that particular key. You know that if that key is not present in the tree, your search procedure is going to return a null node. You simply place your key in that particular null node. So, that means you are always going to insert your key at a null node or at a last level or at a leaf node. So, it is always done by expanding an external node. Right. So, suppose you have a binary an AVL tree. So, this is an AVL tree which you already seen, which satisfies all the properties of an AVL tree, and we are inserting a key whose value is 54 in this binary in this AVL tree. So, we will insert this as though we are inserting it in a binary search tree. So, we will first compare it with the root. It is bigger than the root. So, we will go to the right subtree, compare with root of the right subtree, which is 78, less than that. So, we will go to the left subtree, look at root at the left subtree, which is 50, bigger than 50. So, go to the right, root is 62, less than 62. So, we will reach a null node. Correct. So, our search will take us to this particular node, which is a null node. we will insert value 54 at that particular external node. So, this precisely is a binary. It's now this is precisely insertion in a binary search tree. So, we have inserted key 54 as we would have inserted this in a binary search tree. So, at this particular point, the binary search tree property is satisfied. Let us try to check the height property of this particular tree. If it satisfies the height property also, then there is nothing to be done, then it is an AVL tree. Let us look at the tree with 54 inserted in it. Right. So, we have inserted 54 at this particular point. Now, we will try to look at the path from the node which is inserted to the root and check the height properties at each of the nodes in this particular path. If at all height property is going to be violated, it is going to be at one of the nodes on this path. So, we will look at the node which is inserted and the path from that node up to the root and check height properties at each of the nodes on this path. If at all somewhere it is violated, it is going to be on this path. So, we will start from where the key is inserted and go up to the root in the tree. So, let us start with 54 which is inserted. Now, look at the node which is just above 54. At this particular node, the left subtree has height 1, the right subtree has height 0. So, at that particular node your height property is satisfied. Now, let us go up in the path. At this particular node, the left subtree the height is 1, the right subtree has height 2, correct. So, at this particular node also your property is satisfied. Now, let us still go further up into the tree where the path from the inserted node to the root at this particular node. Now, here the left subtree has height 3, whereas the right subtree has height 1, correct. So, at this particular node left subtree has height 3 and right subtree has height 1. So, the difference is more than 1. So, the height property is violated at this particular node. So, though it is a binary search tree, it is not an AVL tree. So, we need to restructure this tree such that we do not lose the binary search tree property and also have the height property. So, we are going to look at the search and repair strategy. So, our search and repair strategy is going to restructure our tree such that we do not lose the binary search tree property and also the height property or height balance property is satisfied. So, we are going to do some labeling in order to have a unified way of writing our procedure. So, we are going to call Z as the first node encountered in going up from the inserted node towards the root at which the height property is violated. As we said, your height property is going to be violated only at a node which is on the path from inserted node to the root. We are going to say Z is the first such node. We are going to call Y as a child of Z with the higher height and X is going to be the child of Y with higher height. So, we are going to label our nodes as Z, Y, X with these properties. So, if I go back to the earlier example. So, as we said, this was the first node we encountered as we went from inserted node towards the root where height property was violated. We have called this as Z. Now, we look at its left subtree and right subtree. This has height 1 and this has height 3. So, this we are going to call as Y. Similarly, at Y we look at its left child and right child. this has height 1, this has height 2, so this is x. Once we see that where the property is violated, we call it as z. Y and x are identified by looking at their subtrees with a higher height. So, we label z, y, x with this convention. Now, we know that height balance property is violated at z. So, we try to balance the subtree rooted at z. This is going to be called tri-node structuring. Tri-node structuring because we have 3 nodes that are going to be involved in our structuring, that is x, y, z. And also in our restructuring, the subtrees rooted at x, y, z are also going to be important. So, the subtrees that are rooted at x, y, z are also going to be important when we restructure our AVL tree. Those have also been identified here, correct. So, the tree rooted at y, this is called 2, 0. The trees which are rooted at x are called T1 and T2, and tree which is rooted at 88 is called T3. So, our tri-node structuring will involve x, y, z and the trees rooted at x, y, z, which are T0, T1, T2 and T3. So, tri-node restructuring, we are going to relabel x, y, z as A, B, C, such that A precedes B and B precedes C in an in-order traversal of tree. We will see that there are 4 possible cases to do this mapping. We are going to try to give a unified way of restructuring under which works for all the 4 cases. The unified way is going to be as follows. We are going to replace z with the node called B, make the children of this node as A and C while maintaining the in-order relationships of all nodes in T. Right. So, what we are doing is first we are going to label x, y, z as A, B, C, such that A precedes B and B precedes C in order traversal. We will see that there are 4 possible ways of doing this mapping. Our restructuring policy is going to be the same for all 4 cases, and the policy is we are going to replace z with the node called B, make the children of this node as A and see that the in-order traversal relationships are maintained of T. So, let me look at the 4 cases first. So, the first case is like this, A, B, C. So, if I look at the first case, this precisely, if I look at the in-order, so this is, we are precisely trying to look at the part of a tree at which the height property is violated. Right. So, we are showing only a part of a tree at which the restructuring needs to be done. So, in this case our imbalance happens at z, right. So, imbalance will always happen at z. The meaning of x, y, z is not going to change, meaning the labeling A, B, C is going to change. So, what we want is, in this particular case, we want A, B, C as they occur in order traversal. So, we are going to have A here, B here and C here. So, we are going to label A equal to Z, B equal to Y and C equal to X. This is one possible case. The second case is sort of the symmetric part of the first case, in which you have the tree skewed on the left hand side. So, again height imbalance is at Z and you have Y and X. Now, we want in order traversal. Remember, in order traversal is first left child, then root and then right child. So, in this case the first left child is going to be A. So, A is going to be here, B is going to be here and C is going to be here, right. So, this is the second case. Remember, meaning of x, y, z is always going to be the same, that is z is where height property is violated, y and x have their meanings as defined earlier. A, B, C mapping is going to change according to the structure of the tree. this is case 2, and the case 3 and 4 are going to be like this, in which case you still have Z here where the height balance is violated, and Y and X are like this. And if I look at the in-order traversal, you are going to have A, correct, because it is a root, correct. So, you would have seen if I look at the in-order traversal, you would have done all this in in-order traversal, that is the left part of subtree rooted at A, then you would have visited A, then we would have visited B and then C. So, even here again Z is where property is violated. You have A, correct. So, first we will go visit T0 in our in-order traversal, then we will go to A, then we will have B, and then again finally C. So, A is going to be before B and B is going to be before C. So, these are the 4 possible cases that can happen, and in all 4 possible cases our restructuring policy is the same. Now, let us look at our restructuring policy. Right. So, our restructuring policy, which works for all the 4 cases, is replace Z with node which is called B, make the children of this node as A and C, maintain the in-order relationships of the tree T. Let us look at restructuring in the first case. In this case, so we are going to replace this by B, correct. So, this Z is going to be replaced by B, and A and C becomes the child of B. A becomes the left child and C becomes the right child. A has to become the left child because A has to come before B in its in-order traversal. Remember, the in-order traversals here are maintained. That is, if I look at the in-order traversals, correct, you will have T0, then A, then T1, then B, then T2, then C and T3. Correct. So, let us try to look at the in-order traversal. So, in-order traversal is first T0, then we will visit A, then we will visit T1 in order, then we will visit B, then we will visit T2 in order, then we will visit C and then finally T3. So, this is the in order traversal of the tree which is on the left side. Now, after our restructuring, in order we will first visit T0 here, then we will visit A, then we will visit T1 in order, then we will visit B, then we will visit T2 in order, C and then finally T3. So, we see that under our restructuring the in order traversals are maintained. This particular restructuring is called a single rotation, because we see that it is a rotation which happens only once, or we are simply rotating the tree once on the left side, correct. So, we are simply rotating it like this once, that is B is going here, this is going here and this is going here. So, this is called a single rotation. This case is symmetric to the first case, right. So, we have a tree which is now symmetric to the earlier case. In this case, we are going to do a rotation on the right hand side, right. So, this tree is going to be rotated on the right hand side. So, B goes here and this becomes the right subtree and this becomes the left subtree of node B. Again, easy to see that your in order traversals are maintained. So, you have 2 cases of single rotations. Now, we have the other 2 cases which requires what are called double rotations. Right. So, policy is same, this is going to be replaced. So, whatever is this is going to be replaced by, correct. So, in this particular case this is going to be replaced by B, and so this is going to go here. So this is going to rotate once over this and once over this, correct. So that is why it is called double rotations, correct. So B will go to the place of Z, this becomes the left child and this becomes the right child, right. So easy to check that. And similarly the last case, so this node has to go here. Remember, wherever Z is, B has to be B has to move to the place where Z is. So B will go here. So B has to rotate once over this and then over this, right. So B will go here, this will become the right child here and this will become the left child. It can be easily seen that your in order traversals are maintained in the restructuring. What can be shown is that the restructured tree satisfies the height balancing property. So now let us look at the example that we were looking at. So we had already identified, if you recollect, Z, Y and X. So this precisely corresponds to, correct. So if I look at if you look at our 4 cases, this precisely corresponds to case where your Z is here, Y is here and X is here. So it corresponds to the last case in our of our 4 cases. So that requires a double rotation. So to restructure our tree so that the height property is maintained, we are going to use this particular double rotation. So this has to go here. So let us go back and check where our B was. So in this case your B is here, correct. So B is at X and A is Y, correct. So let us identify that also. So once you have identified this, correct, so this is B, correct. So we have seen that this happens to be B. So under our restructuring, B has to go at this particular point. So this node 62 will go here at this place. This things will come as the left subtree and this things will come as the right subtree. Right. So this particular example, it fits into the 4th case of our restructuring. Once we do this, it is easy to see that your height property is satisfied, right. So we just check at this point. At this point now, if the left subtree has height 2 and the right subtree also has height 2. So the height property is satisfied. Once it is satisfied at this particular place, we know it is also going to be satisfied at all the places above that, right. So the procedure will stop here. Right. So we have seen how we are going to insert into a AVL tree. Okay. Thank you.